Recent scientific discussions suggest that time might not be the fundamental backbone of reality we once thought. Instead, it could be an emergent phenomenon arising from the mysterious world of quantum mechanics. This revelation challenges our deepest intuitions and has profound implications for physics and our understanding of the universe. In this video, we will explore what this means, the science behind it, and why it matters so profoundly. Traditionally, time has been viewed as a constant and ever-flowing river, moving uniformly from the past through the present and into the future. In classical physics, time is an absolute backdrop against which events unfold, independent of the observer or the events themselves. This perspective was famously encapsulated by Sir Isaac Newton, who described time as absolute, true, and mathematical, flowing uniformly regardless of external factors. This Newtonian view held sway until the early 20th century, when Albert Einstein introduced his groundbreaking theories of relativity. In his special theory of relativity, Einstein proposed that time is not a universal constant but is relative, varying with the observer's state of motion. He demonstrated that as an object approaches the speed of light, time for that object slows down relative to a stationary observer, a phenomenon known as time dilation. This was a radical departure from Newtonian mechanics, suggesting that time is intertwined with space, forming a four-dimensional continuum known as spacetime. Einstein's general theory of relativity further revolutionized our understanding by showing that gravity is not a force acting at a distance, as Newton had proposed, but a curvature of spacetime caused by mass and energy. In this framework, massive objects like planets and stars warp the fabric of spacetime, and this curvature dictates the motion of objects and the flow of time. For instance, time runs slightly faster on a mountaintop than at sea level because the strength of Earth's gravitational field decreases with altitude. This effect, though minor, has been confirmed by precise measurements using atomic clocks. These relativistic effects are not just theoretical musings, but have practical implications. GPS satellites orbiting Earth experience both reduced gravity compared to the planet's surface and high velocities relative to an observer on the ground. According to Einstein's theories, the reduced gravity would make the satellite clocks run faster, while their high speed would make the clocks run slower. The net effect is that time on these satellites runs slightly faster than on Earth's surface. If uncorrected, this discrepancy would lead to navigational errors accumulating at a rate of about 10 kilometers per day. To ensure accuracy, GPS systems account for these relativistic time dilations, adjusting the satellite clocks accordingly. Despite these revelations, both Newtonian mechanics and Einstein's relativity treat time as a fundamental dimension. Whether absolute or relative, time is a given, an intrinsic part of the universe's fabric. In quantum mechanics, time is often treated as an external parameter, a backdrop against which the probabilities of different outcomes evolve. This treatment contrasts sharply with the relativistic view, where time is intertwined with space and influenced by gravity. One of the most intriguing phenomena in quantum mechanics is entanglement, where particles become so deeply connected that the state of one instantaneously influences the state of another, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, has been experimentally confirmed and suggests that information can be correlated across vast expanses without any time delay. Such instantaneous connections challenge the classical notion of causality, which relies on a temporal sequence of cause and effect. Recent studies propose that time itself might emerge from quantum entanglement. The Page and Wouters mechanism, introduced in 1983, suggests that for an entangled system, time emerges through the correlation between subsystems. In this framework, one part of the system can act as a clock, and its entanglement with another part gives rise to the perception of time's passage. Without such entanglement, the universe would appear static and unchanging, implying that time is not a fundamental entity, but a manifestation of quantum correlations. This perspective aligns with the Wheeler-DeWitt equation in quantum gravity, which intriguingly omits time altogether. The equation describes the quantum state of the entire universe, suggesting a timeless wave function of the universe. In this view, time emerges only when considering subsystems in relation to each other, reinforcing the idea that time is not a fundamental backdrop, but an emergent property arising from the entanglement and interactions of quantum states. The concept of emergent time challenges the traditional separation between space and time in relativity and the fixed parameter of time in quantum mechanics. It suggests that a deeper, more fundamental theory might exist, one where space-time and time itself emerge from more basic quantum processes. Such a theory could potentially resolve the long-standing conflicts between the two pillars of modern physics, paving the way for a unified understanding of the cosmos. Understanding time as an emergent phenomenon also opens new avenues in fields like quantum computing and information theory. If time arises from quantum correlations, manipulating these correlations could lead to novel ways of processing information, potentially revolutionizing technology. This notion challenges deeply held beliefs and forces us to confront questions about the nature of reality, causality, and consciousness. Traditionally, reality is seen as a sequence of events unfolding in time, a progression from the past through the present and into the future. However, if time emerges from quantum correlations, then reality might be more like a static block where all moments coexist, and our perception of now is a construct of our minds. This view aligns with Einstein's relativity, which posits that all points in spacetime are equally real, eroding the idea of a universal present. If true, reality itself may not be as dynamic as it feels, but instead a subjective construct shaped by human perception and interaction with the universe. The concept of emergent time could revolutionize efforts to unify quantum mechanics and general relativity, two of the most successful yet incompatible theories in modern physics. General relativity treats time as a dynamic entity influenced by gravity, while quantum mechanics treats it as an external parameter. Emerging theories like string theory and loop quantum gravity suggest that space-time, and by extension time itself, may not be fundamental, but arise from deeper quantum structures. For example, string theory proposes that time may emerge from the vibrational patterns of fundamental strings, blending seamlessly with the fabric of spacetime. Loop quantum gravity suggests spacetime is composed of discrete chunks, with time arising from their interactions, while in the Wheeler-DeWitt equation, time is absent, implying that the universe can be described in a timeless state, with time emerging only when considering subsystems in relation to each other. These ideas suggest a paradigm shift in physics, where time is no longer a fundamental variable, but an emergent feature of a more profound, unified theory. Time's emergent nature invites intriguing questions about the role of human consciousness in shaping our experience of time. Some theories propose that our brains impose a sense of flow and causality onto a timeless quantum reality. Neuroscientific studies reveal that the brain organizes sensory inputs to create a coherent narrative of past, present, and future. This mental time travel is crucial for survival, enabling us to anticipate threats and plan for the future. However, if time is an illusion, it raises questions about the relationship between consciousness and the physical world. Could our perception of time be a survival mechanism rather than a reflection of objective reality? And if so, what does this mean for concepts like free will and causality? The implications of emergent time extend beyond physics into philosophy and daily life. Philosophically, it challenges the concept of free will. If all moments in time coexist as suggested by the block universe model, then our choices might be predetermined, with the sense of freedom merely an illusion. Thank you for watching. We hope you enjoyed this exploration into the fascinating concept of time as an emergent phenomenon. If you found this video insightful, don't forget to like, subscribe, and share your thoughts in the comments below. Stay curious, and we'll see you next time for more captivating discussions on science and the mysteries of the universe.